Welcome to this deep dive into the realm of quantum computing. Perhaps you have heard the buzz about how quantum computers could revolutionize everything from cryptography and data analysis to drug discovery and machine learning. In this video, I will explain what exactly differentiates a quantum computer from the classical machines we all know, why quantum bits, qubits, are so different from normal bits, and how phenomena like superposition and entanglement empower these futuristic devices. We will also discuss why creating a stable quantum system is incredibly challenging, yet equally rewarding. Before we begin, please remember to like this video, subscribe to our channel, and hit the notification bell so you won't miss future explorations of groundbreaking technologies. To start, consider your everyday computer, a classical device that stores information in bits, each bit being either a 0 or a 1. This binary logic underpins everything from smartphones to giant supercomputers. A quantum computer, however, harnesses quantum bits called qubits. A qubit can be in state 0, state 1, or something far more interesting, a superposition of both 0 and 1 at the same time. This quantum mechanical principle of superposition grants qubits the ability to represent multiple configurations simultaneously, at least until a measurement forces them to collapse into a definite 0 or 1 outcome. The mathematics behind it uses complex amplitudes to describe probabilities, making quantum computing fundamentally different from the digital on-off nature of classical computing. Another key aspect is quantum entanglement, which Albert Einstein famously criticized as spooky action at a distance. If two qubits become entangled, their states intertwine so that measuring one qubit instantly affects the state of the other, no matter how far apart they are. This phenomenon flies in the face of everyday logic. Nonetheless, it is one of the most rigorously tested predictions of quantum mechanics and forms the basis of the extraordinary parallelism we hope to exploit in quantum computing. By entangling multiple qubits, one can effectively make them act as a single quantum system. This allows certain algorithms to achieve exponential speedups over classical methods. If n qubits are all entangled, you have a quantum state that, in principle, encodes 2n amplitudes simultaneously. That does not automatically mean you can read out 2n classical results at once. Measuring disrupts the system, but it does let you perform transformations on these superpositions that can cancel out wrong paths and reinforce the correct ones. Why do we not already have quantum machines everywhere? One significant obstacle is decoherence. Quantum states are extremely delicate. A single stray photon or a bit of heat can collapse a qubit superposition, destroying the quantum information. This is why quantum processors often operate at temperatures near absolute zero, inside specialized cryostats that shield them from environmental noise. Even so, qubits remain prone to random errors, meaning quantum error correction is essential. Quantum error correction requires extra qubits solely devoted to detecting and correcting errors, which balloons the total number needed to do anything practical. Overcoming decoherence and implementing error correction robustly is one of the biggest engineering feats of our era, making the development of large-scale quantum computers both expensive and profoundly complex. Let's talk about the hardware strategies that researchers and companies use. One prominent approach is the superconducting qubit, employed by IBM, Google, and Rigetti, among others. Here, tiny superconducting loops at millikelvin temperatures create quantized energy levels that act as qubits. Another method is ion trap technology, used by IonQ in academic labs, where individual ions are suspended in an electromagnetic field in a vacuum. Laser pulses manipulate their internal states to form qubits, which can have excellent coherence times, but pose challenges in scaling to large systems. There are also photonic approaches, using single photons as qubits, spin qubits in silicon, and topological qubits. Each approach seeks to maximize coherence times, reduce errors, and make it possible to combine thousands or millions of qubits into a single machine. Now we come to the algorithms. Classical bits can be processed with AND or NOT gates, whereas quantum gates manipulate superpositions and entangled states. Researchers have discovered a handful of quantum algorithms that demonstrate a potential for dramatic speedups. Perhaps the most famous is Shor's algorithm, which factors large integers in polynomial time. This threatens classical public key encryption, like RSA, as factoring very large numbers becomes feasible once a quantum computer has enough qubits and error correction to run the algorithm reliably. Another well-known quantum algorithm is Grover's algorithm for unstructured database search, which offers a quadratic speedup. Although it's only quadratic, for extremely large datasets, that advantage can be quite meaningful. There are also specialized methods for simulating quantum physics or chemistry. Since nature is inherently quantum, simulating quantum effects on a classical machine is often intractable, but a quantum computer can theoretically handle such tasks more directly by encoding quantum states in the hardware itself. One buzzword is quantum supremacy, also called quantum advantage, the point at which a quantum computer solves a problem beyond the feasible capacity of any classical computer within a reasonable time. In 2019, Google claimed to have achieved quantum supremacy on its Sycamore processor by performing a random circuit sampling task in just a few hundred seconds, which they argued would take the best supercomputers thousands of years. IBM and others disputed the exact numbers and argued for possible optimizations, but the moment signaled that quantum computing is no longer mere speculation. True, the demonstration targeted a very specific problem. Achieving universal quantum advantage across real-world tasks still requires more robust and larger machines. Yet progress is tangible, suggesting that we could be near an inflection point in computational history. If quantum computing is so powerful, how would it affect everyday life? Many experts predict that in the next decade, quantum machines will help solve specialized tasks in chemistry, materials design, cryptography, optimization, and even AI. Instead of a personal quantum computer sitting on your desk, it's more likely you'll access a quantum cloud service, where a specialized quantum coprocessor performs computations that would be otherwise impossible for your local device. This would reflect the HPC, high-performance computing, or GPU-accelerated model we already see, but with far more delicate hardware. A big looming concern is security, since large quantum computers could break many current encryption schemes, forcing an industry-wide shift to post-quantum cryptography. Governments and companies already invest in these next-generation encryption methods to safeguard data against future quantum attacks. Why do we call it a revolution? If we can solve certain computationally intensive problems exponentially faster, entire fields might leap forward. Quantum simulation alone could unravel new superconductors, speed up drug discovery by simulating molecular interactions at a quantum level, or yield better catalysts for energy production. Optimization tasks in supply chains, finance, or traffic flow might see significant improvements. That said, quantum computers will not magically accelerate everything. They excel at particular classes of problems that exploit superposition and entanglement. They do not necessarily run your operating system or web browser more efficiently, so they likely will not replace classical machines entirely, but complement them in a hybrid approach. Building a fully error-corrected universal quantum computer remains a formidable challenge. Each qubit must maintain coherence long enough to perform complex sequences of gates, while the system overall must remain stable. The more qubits you have, the tougher it becomes to protect them from noise. Currently, many labs achieve just tens or at best a few hundred noisy qubits, yet meaningful quantum applications beyond specialized demonstrations may require thousands or millions of logical qubits, once error correction overhead is accounted for. This mismatch between hardware reality and theoretical needs underscores that quantum computing is a young field. Major leaps forward in technology, theory, and engineering are all needed. Meanwhile, quantum annealers like those from D-Wave implement a different quantum mechanism, focusing on solving certain optimization problems by letting the system settle into low-energy states. Though they are not universal gate-model quantum computers, they have shown some promise in specialized optimization tasks. So there is not just a single type of quantum computer. Multiple approaches exist, each with a unique design philosophy. At the end of the day, the fascination with quantum computing stems from its potential to push boundaries that classical computing cannot easily cross. Whether we speak about exponential speedups for factoring large numbers, simulating quantum chemistry, or accelerating machine learning, the mere existence of these possibilities is extraordinary. On the flip side, controlling and scaling such a machine is an engineering feat possibly as great as humanity's biggest physics experiments. Governments worldwide, from the US and China to European nations, have recognized the strategic importance of quantum technologies, pouring billions into research and development. Tech giants, startups, and academic labs compete to refine hardware and algorithms, hoping to be the first to reach robust, large-scale quantum computing. One should note that quantum computing, while powerful, is not a silver bullet for all computational tasks. Many problems do not gain huge benefit from quantum speedup. Nonetheless, the scope of applications that do stand to benefit is substantial, ranging from cryptography and advanced optimization to drug design and climate modeling. Already, some specialized quantum software frameworks allow developers to prototype quantum algorithms using Python or other languages, often running on simulators for up to a limited number of qubits, or on real but small, noisy quantum devices in the cloud. Progress is swift, and the next decade may witness a surge in quantum-based solutions that rewrite the rules of computing in certain niches. In summary, a quantum computer harnesses qubits, which exploit superposition and entanglement to process large amounts of information in ways classical systems cannot replicate. The technology's potential is vast, but current implementations are noise-prone and small-scale. Researchers worldwide are striving to overcome decoherence, develop quantum error correction, and scale these machines to the thousands or millions of qubits needed for practical universal quantum computing. It's an endeavor that merges physics, computer science, materials engineering, and more. I hope this long explanation has given you a solid understanding of what quantum computing is and why many people consider it a transformative leap for our digital future. If you have any questions or opinions, maybe you're intrigued by the superposition concept or worried about encryption being broken, feel free to post them in the comments. Don't forget to like this video and subscribe to our channel for more explorations of leading-edge science and revolutionary technology. Thank you for watching, and I look forward to seeing you next time for another deep dive into humanity's most ambitious endeavors.